Now that I know what it means to be orthogonally diagonalizable, I can try and prove the theorem. Okay? We're going to prove that if A is orthogonally diagonalizable, it has to be symmetric. So what we do is we take an orthogonal matrix Q and a diagonal D such that well, A equals Q D Q. Well, how about I write Q transpose? Are you guys okay with that? Why? Yeah, that's another fact about orthogonal matrices, which is a really handy fact. Because usually computing the inverse is a pain, but it's easy if you have an orthogonal matrix. So we're going to do that. Okay, so what do we want to prove? Prove that A is symmetric. How do you do that? Well, we need to show what? That A equals A transpose. So let's think about A transpose. Well, A transpose equals Q D Q transpose transpose. We just said that that's how we can write A. Now what am I going to do next?
Apply the transpose to their answer.
Yeah.
Like back in the group, so Q, E transpose, Q transpose. Does that work? Does that work the same way as inverse?
It works the same. It's that shoes and socks thing again, right? So I'm going to write this as Q transpose transpose. That's the last one. D transpose Q transpose, right? That's the shoes and socks thing. And by the way, what's Q transpose transpose? That's Q. And what's D transpose? What happens when you take a diagonal matrix and you transpose it? It's the same as D, right? And then I have Q transpose, and what's beautiful about what I just wrote? That's equal to A. What a lovely proof that is. Done. Okay? So we proved that if A is orthogonally diagonalizable, then it is symmetric. Now, the other way, that's theorem 5.20, and it's what your book calls the spectral theorem. Well, actually, the spectral theorem, so if you're looking to what was the answer to today's quiz question, it was the following. Let A be a real n by n matrix then A is symmetric if and only if A is orthogonally. Oh boy, I can see why you had trouble spelling. Let me try that again. A is orthogonal, double the L-Y, diagonalizable. Wow, this is great. A is symmetric if and only if A is orthogonally diagonalizable. So the point is, this direction is easy. We did it in 2 lines. The other direction is not. And that's what the rest of the chapter is about. Okay, so when I said I think that you could use some help, it's really the other direction that I thought, let me see what I can help you with. Okay?
Do you have to use the decomposition of it to get to it?
Well, yeah, I mean, that's what I'm given in a sense, right? And so yes, we will use the decomposition. And we also need a few other facts, okay? And by the way, you'll notice when we proved 517, we didn't say that A was a real matrix. Do you guys know what I mean by a real matrix?
No imaginary numbers.
No complex numbers, no imaginary numbers anywhere in it, okay? That's going to be important for us. If you want to put the word complex in here, you might remember when I gave my talk, I had a whole bunch of other vocabulary. I used the word unitary instead of orthogonal for these matrices, and that just involves the complex conjugate, and it's getting really annoying at that point, so we're just going to stick to this. Okay, but there is a theorem like it. A is Hermitian if and only if A is... we'll just do this. We'll stick to the real. Keep it real, like I tell my calc students. Okay. So along the way are two other theorems. So let me state them. Theorem 5.18. If A is a real symmetric matrix, then the eigenvalues of A are real. Now, I guess I have a question. Have we come across matrices in this course that have eigenvalues that are not real? We have. Have they been real matrices sometimes? And that answer is yes. But the point is symmetric. If it's symmetric, they're going to be real. They're going to be just, on the complex plane, they're going to all show up here. I actually used that fact in my talk also. I had this thing called the field of values that contained the eigenvalues, and the whole field of values ends up being right on the real line if your matrix is symmetric. Okay. So that's a nice theorem to know, especially because, right, we're saying we're going to have real symmetric matrices. Okay. Right? And then we're going to try and come up with this decomposition. So, the proof? No, too technical. Well, too technical to be interesting. One time I proved it in class, and about halfway through, I looked at my class. I said, why did I do this? Okay? So I will not do that today. You can look in the book. If you want, or if you want to stop by, I can help you with it. But it's just pushing a lot of lambdas and v's around. And let's move on. If you were taking a complex numbers course, it might be worth it. But we're not. We're taking linear algebra. All right. Theorem 5.19, I think I will prove today. This was on the fence. I was like, should I or not? I want to. If A is a symmetric matrix. And again, that's what we're going to assume, right? We're going to be going the other direction right now. If A is a symmetric matrix, then any two eigenvectors, EVs we've been calling those with a little bar, corresponding to distinct eigenvalues are orthogonal. That's really cool, actually. I mean, right here I could stop and get an example from the book, that'd be great. Let me pause. Yep, we're going back to the very beginning. The first few examples we did all came from this. Yeah, and I remember we skipped this example because it was 4 by 4, and we didn't know how we were going to. Although we were able to show that these things are fixed vectors. How do you do that? You just take the matrix times the vector, right? And that means it has an eigenvalue of what? 1. And then later, we came up with V4. What's that? I should do that real quick. So if I do this matrix times 1, 1, 1, 1, I guess I'm going to get 2, 3, 4. I'm going to get 5, 5, 5, 5. So that means that this one corresponds to the eigenvalue 5. The other ones correspond to the eigenvalue 1. Is it true that these are orthogonal? Yeah. If you dot any of these eigenvectors with this one, do you see how you get 0? Okay. What if you dot, say, this one and this one? Then you don't get 0. So the eigenvectors that correspond to the same eigenvalue might not be orthogonal. You could make an orthogonal basis for this 3-dimensional eigenspace. Now we know how. But that's not guaranteed. But this is guaranteed. That's kind of nice. By the way, while we have this out, I just thought I would remind you, here's our first example we had of a complex eigenvector, right? I don't remember if the eigenvalues were complex. I think so, because the characteristic polynomial would be lambda squared plus 1. So the eigenvalues are plus or minus I. Yeah. But this is not real symmetric. This is just real. This is actually skew symmetric. Here's one that's real symmetric. Those have to be all these nice properties. If I want to prove this, I need to show that any 2 eigenvectors are orthogonal. So probably I'm going to take 2 eigenvectors and dot them. Right? That's what I'm going to do. Okay, so here I go. Proof. Let V1 and V2 be eigenvectors. It's good to have shorthand. Corresponding to the eigenvalues, and I'll say they're lambda 1 and lambda 2 respectively. And I'll say lambda 1 does not equal lambda 2. Okay. So we have a V1 equals what?
Lambda 1, V1.
Yep. And we have a V2 equals lambda 2 V2. That's what it means for those to be both eigenvalues and their corresponding eigenvectors. Okay. So how the heck do we do this? How do we show that the dot product is 0? Well, here's the trick. We're going to take lambda 1 times V1 dot V2. Now you have to be really careful when you write out this equation, because what the heck are we doing? We're dotting. We want to show that this dot product equals what? 0. I have lambda 1 here. And now, here's a property of dot products that, well, the reason this works for us is because we understand that a dot product, really, if you want to, you can think of this as V1 transpose V2, right? And so if I have a scalar times a product of matrices, you can just take the scalar times 1 and then do the transpose, right? So every time I write dot, remember that it could be just a matrix multiplication where you put a transpose there. Okay? So far, so good? What do you think I'm going to do where it says, oh, this should be lambda 1, right? What do you think I'm going to do where it says lambda 1, V1?
AV1.
We're going to call that AV1. That's right. AV1. Now, what is AV1? It's a vector. So we can dot it with V2. This is all making sense so far. And remember that a dot product, like I said, is really a transpose. Do the transpose and then multiply the matrices. Okay, next. Shoes and socks rule. V1 transpose, A transpose, V2. I guess I should really have this in parentheses. Is that okay? But now I'm going to move the parentheses. I'm going to write it this way. V1 transpose. And over here, I'm using the associative property, but I'm also just going to write AV2. I'm not going to write A transpose anymore. And how do I get away with that? A is symmetric. Okay. So from here to here, we're using associativity, and we're using the fact that A is symmetric. Laura, okay? You all right? Now what? What do you think I'm going to do with AV2? Let's call it lambda 2 V2. V1 transpose, lambda 2 V2. And now, I'll pull the lambda 2 out front. So what I have is lambda 2 V1 transpose V2. And that's lambda 2 V1 dot V2 if you want. Okay, because again, transpose means dot. Sure. Let's see what's going on here. So what the heck did I just do? I basically did a whole bunch of manipulation, and I got that lambda 1 times V1 dot V2 is exactly equal to what? Lambda 2 times V1 dot V2. So now we can subtract, and we get, well, lambda 1 minus lambda 2 times V1 dot V2 equals 0. Right? You factor out the V1 dot V2 and you have this. Lambda 1 minus lambda 2, that's a number. V1 dot V2, that's a number. Two numbers multiplied to equal 0. What's that mean? One of them 0. But we know, since lambda 1 does not equal lambda 2, right, we get V1 dot V2 equals 0 as desired. It's a pretty cool proof.
decided V1 to V2 to begin with?
That's the toughest part of the proof. Who thought of doing this in the first place? Well, I think it's very natural to think of V1.V2, because what are we trying to prove? Trying to prove that the eigenvectors are orthogonal. Okay? So to do that, I think, is natural. The eigenvalue comes into play here. Here's the thing. Who thought of putting one eigenvalue here and another, and getting it to equal the other eigenvalue, and then that would then give you the proof? To me, that's clever. Although I have to tell you, I've seen this type of proof numerous times in various math classes. You're trying to show that something equals 0. You get a product to equal 0. You know the one doesn't equal 0 because they're not equal, and you get the other. I mean, there's a reason I decided to show you this. It may come up again if you're taking more math classes in your future. But you're right. I mean, that's the clever part. Who came up with that? But just knowing it's a proof by induction might be enough. I don't know. Like I said, I want to pause, and we'll figure out what to do after break. I have to say, you guys are getting me excited about the end of the course.
Is that a bad insult?
No, that's not what I mean by that. I said that wrong. Not that I'm excited about the course ending. I'm excited about the end of the course. I mean, in the last few weeks here. I feel like we're learning quite a bit, and I feel like opportunity is here too. That's not you guys. This is you guys. So, as I was looking at the proofs we were doing today, right? I hope that now you at least have an idea what orthogonal diagonalization of symmetric matrices means, okay? And we proved that if it's orthogonally diagonalizable, then it's symmetric. That was easy. To go the other way is a lot of work, and I gave you some of the building blocks we would need, and I told you it's a proof by induction, and that's it. And you'll notice I only assigned 3 homework problems. Okay? I thought I might give a sample problem just to kind of show you what we're dealing with here. Okay? The thing I sometimes do is number 27. But I didn't. Okay? So yeah, let me pull out the book and just kind of show you what it is we're talking about here. Okay, so I guess I want to give you just a few hints for the homework for Wednesday. That's really what I want to do here. Okay? Number 27 is not required. It's the kind of thing that some of my students have done sometimes. And I'll explain what that is in a minute. As a matter of fact, some of you are still trying to figure out what you're going to do for your project. This could be a component of the project. Okay? I still haven't handed out anything formal yet for the project. I've been having conversations. And that's what's getting me excited, I think, are the conversations, because you guys have lots of good ideas. But again, the project, okay, this time is 30 points. Right? And so what I said was we were going to divide it up. 10 points would be for another presentation. But per your request, we said we would give you up to 10 minutes, right? And then I have 2 10-point components. Okay? And so I wanted you to pick something out that has linear algebra in it. You don't have to write this down because I'm going to have a handout. But I also really wanted to get you into some MATLAB. So some linear algebra application and some MATLAB. And what we've been finding is this. Some of you it's been very easy to find a linear algebra application you're interested in, but you've had trouble even thinking about the MATLAB. And I hope I'll be able to help you with that, with what I'm going to show you in a second. Some of you, it's been very easy to think about MATLAB, but it's been tough to really find a linear algebra application. Okay? Well, let me just suggest number 27 as another linear algebra application that you could kind of throw in the mix if you need some linear algebra for your project. Okay? Because what it is, it's something that I think any of us could do. All right? The spectral theorem, again, this is kind of the highlight of the book, right? We just talked about it. A is symmetric if and only if it is orthogonally diagonalizable. So you're going to start off with it symmetric. And you could spend some time reading through, stopping by for help if needed, and work through this proof by induction. And if you did, you'd be all set for number 27. Now, what's number 27 say? Let me zoom in on it. Let A be an n by n real matrix, all of whose eigenvalues are real, so keep it real. Prove that there exists an orthogonal matrix Q and an upper triangular matrix T such that QTAQ is T. You can orthogonally triangularize. How about that for some vocab I just made up on the spot? You can orthogonally triangulize any real matrix. It's a lot like the spectral theorem, but what hypothesis is missing now? In the spectral theorem, you have a real symmetric matrix. Here, you just have a real matrix. And you can orthogonally triangularize it. And so really, when they say hint, adapt the proof of the spectral theorem, you could cross out that word adapt and almost put copy, and that almost is it, okay? But not quite. But I think it would be a good linear algebra exercise to try and learn the proof of that theorem by adapting it here. I'm just going to throw it out there, okay? If you're a person that's struggling to find, I can't find any linear algebra I want to do. Now, what if you're one of the people that's struggling to find MATLAB? Interesting at all. Ick, computers. Let me show you what I have here today. So I have a book by Cleve Moeller, who actually is one of the inventors of MATLAB, if I'm correct. He definitely works for the company. And this ebook is copyright 2011, the most current edition, but he's been working on it for years. And if you notice some of the topics that are in here, Tony, Fibonacci numbers, and magic squares, two things you've been thinking about. Okay. Laura, ordinary differential equations. Okay. Orbits. These are not planet orbits, although I have a really cool thing to show you, speaking of. Some people were interested in the Google matrix. There's a nice little demo about that here. Actually, just exploring the matrices chapter would get you some linear. There are some things here that don't do any linear. That's one downside. This may help you fulfill your MATLAB requirement, and it may or may not help you fulfill the linear aspect of it. It depends which chapter you're looking at. But it's more than just a book. There's a link. Oh, there's Morse code. I mentioned that. There are links. And then there's this beautiful picture, which is actually a piece of MATLAB software. It's an interface. EXM is Experiments Moeller GUI. Anyways, you go here, you download the book for free. I guess I could put a copy on my Blackboard page for you. Or the other thing that I'm looking into is, since we all have the virtual desktop, I'd like to just put everything on the desktop. That's a work in progress, but I'm hoping by the time you actually need it, it'll be there. Okay? I was talking to them today. Anyways, they give you instructions on how to do this. I don't want to give you the instructions right now, but I want to just show you what it does. So if I run exmgui on MATLAB, because I've already downloaded it, pretty cool things happen. Like, hey, look, this thing pops up. And so while you're reading the textbook and working on the exercises, etc., if you happen to be doing the Magic Square chapter, Tony, you'd click on this and really cool things happen. Or if you wanted to do the piano one, the music one, or Google PageRank. Let me click on orbits. That's what I was going to do. This one is not particularly enlightening at first glance, but, well, as the years go by, we're looking at the solar system, and, you know, we can zoom in, and let me zoom in with the in button. Oh, this is the speed I turned up. I don't want to do that. Turn the speed down. There we go. I can zoom in and look at places, or I could just limit myself to one of the axes. That's kind of nice. So it's really taken advantage of the power of the graphics behind MATLAB. And I think you guys should explore it. I just think it's too great of an opportunity not to dive in a little bit more. And that's why I want that extra component of the project that we didn't have the first time around. Okay? So, anyways, this is coming at you. Okay? This is something that I will be throwing at you. However, we do have chapters 4 and 5 to master, right? And as agreed, or maybe contested, I don't know which way you felt, but as has been decided by the powers that be, we're taking exam 2 a week from Wednesday, right, on chapters 4 and 5. Which means a week from today we got to have that review done, and that's kind of where we stand, right? So, let's see. I'm going to do a homework exercise here. Oh, and then, yeah, I mentioned, oh, I'm sorry. I do remember what I was doing. I mentioned 27 from chapter 5, but I also just want to maybe quickly highlight the other exercises. What's going on here, okay? 5.4, it says, if we read, let me zoom out a little bit. They're asking me in these exercises, try to orthogonally diagonalize these matrices by finding an orthogonal matrix Q and a diagonal matrix D such that QTAQ equals D. So I sure hope they gave me symmetric matrices, right? They have to, otherwise you can't do it, right? So if you have a symmetric matrix, the question is, how do you orthogonally diagonalize? And I think the examples are very easy to follow. I do. Here's example 5.18. Symmetric matrix. Hey, this looks a lot like the one that we just dealt with, right? It has eigenvalues 4 and 1 instead of 5 and 1. Its one eigenspace is only 2-dimensional instead of 3-dimensional. And what do we know is going to be true about these eigenvectors? They're already orthogonal, so that's nice.
But the 2 and 1 are not.
Right. We need 3 orthonormal eigenvectors. So we apply Graham-Schmidt to these two, right? And so we'll get a new vector, and the new vector is still going to be orthogonal to the other one. It's still an E1. And so then the only thing left to do is normalize everything. So they do. They divide. Am I right that I kind of can point you to these examples? Well, I'll find out Wednesday when I see the homework. I think you can do those 3 problems. Maybe one more thing to mention. Yeah, this is kind of cool. When they take these eigenvectors and they write them as columns, they're going to label them Q instead of V because now they're normalized. So lowercase q, these are normalized. And then This is a really cool equation, but I just think it'd be smart for me to wait until Wednesday to talk about it after you've played with this a little bit, example-wise. The projection form of the spectral theorem, yeah. So maybe I'll wait on that just a tiny bit. What MATLAB you want to do, but don't know what linear algebra? Approximating eigenvalues with the QR algorithm. This is something that I'd be able to help you with some, I think, if you needed it. Remember, Q and R, we kind of learned it's a factorization, and we can do it. And the question is, why do you want to? And the answer is, it's another way to approximate eigenvalues. So if that's interesting at all, keep it in mind. What was 5.2 number 5? They gave me a W, and they want to talk about W perp. So they say W is the set of vectors x, y, z. So we're in R3 here, such that x plus y minus z equals 0. Is that what they said? Or did you guys have a different one? Oh, that's number 3. We didn't have 3. I could do that one next if we wanted. 5. W equals the set of vectors in R3 such that, oh, okay, they did this. X equals t, y equals negative t, and z equals 3t. So what set in R3 are they describing? You're not allowed to say it. You're already there. What is this, guys? Okay, he said line. Line through the origin, right? These are the, in Calc 2, I think, at the very end, you call them the symmetric equations. No, not symmetric. Parametric. Ah, that's why they call them parametric equations, because there is one what? Parameter. The one parameter is the one free variable. That's a one-dimensional set. Okay? So if I had to draw it, if I had to draw W, well, I would come out 1 in the x direction and back 1 in the y direction. And then I'd come up 3 in the z direction. And so I'd probably try to draw this rectangular prism. And then I'd say, okay, this is the line. It goes from the origin to that corner of the rectangular prism. That's W. We'll see if my television audience at home likes my drawing. I think it's pretty good, considering it's monochromatic. So now, W perp, well, it's going to be how many dimensions? 2-dimensional. Laura, are you with me or no? Trent? Mike? Tell me. 2-dimensional, right? So it's a subspace through the origin, which is, now how does that look perpendicular to the line? Wow. I'll just pat myself on the back. No, it really doesn't. But I'm trying. Anyways, that's W perp. It's a plane containing the origin. And I remember learning in Calc 2 that if I have a plane containing the origin, or maybe it was Calc 3, yeah, Calc 3, the vector that pops out of the plane and is perpendicular to it is called? What kind of vector? Rhymes with cormal? Normal. Yeah. So that's the normal vector. And I also remember learning that if you have the normal vector of a plane, that you really have the equation. So remember, this normal vector is the same thing. It's basically a basis for W. My normal vector, and this is like in Calc 3, would be 1, -1, 3. So the plane containing the origin would be x minus y plus 3z equals, and then you have to put the right d here. But since it contains the origin, 0, 0, 0 has to equal 0. So there you go. W perp is the set of all x, y, z such that that's true. I think that's what they wanted. I think they just wanted the equation of the plane, or an equation of the plane. There's infinitely many equations, of course. Hey, what if I said find a basis for W perp? Could you do that? Sure, but maybe not when I assigned the homework you couldn't. Well, actually, you should be able to. You just have to find two vectors, right, that are linearly what? Independent. Okay? Can you find one vector? I don't know. How about I put 3, 0, -3, 0, 1? That would work. Get two vectors. And then if I said find an orthogonal basis, well, now that you know Graham-Schmidt, you could do that also. And that would be good for projecting onto W and W perp like we do later. So here we go. 5.3. Number 7. It says V is the vector 4, -4, 3. It says find the orthogonal decomposition of V with respect to the subspace W. Okay, so what is W?
So,
Yeah.
in the previous problem, we found what V1 and V2 were,
Oh, cool.
and I'll give that to you as soon as I find out.
Yeah, because we did exercise 5. So for W, it says the given vectors form a basis for W of R3 or R4. Okay, apply the Graham-Schmidt process to get an orthogonal basis. So W, okay, so yeah, I guess in number 5, we say W is the span of these vectors. X1 equals 1, 1, 0, and X2 equals 3, 4, 2. Okay, so that's W. And now,
If you want, I can just give you what V2 is.
oh, okay, so then you did Graham-Schmidt to it?
Yeah.
So you said, using Graham-Schmidt, and that'll give me an orthogonal basis. V1 equals, did you keep it 1, 1, 0?
Yeah.
Okay. And then V2, of course, that's going to change this. We're going to project that, subtract, and all that. And what do we get?
-1/2, 1/2, 2.
Okay, and I guess I could check that if I dot these, I get 0, so that's good. Now, this is not an orthonormal basis, it's an orthogonal basis, right? Okay, so now in exercises 7 and 8, find the orthogonal decomposition of V with respect to the subspace W. Okay. I guess if I want an orthonormal basis, then I'd want to change those to Q's, but I'm not sure I need that. Not for this. Okay, so now what are we going to do? All right, so the idea now, number 7, when they say find an orthogonal decomposition of V with respect to W. What we're going to do is we're going to write, that means write V equals little w plus little w perp, okay, where little w is in W, and then w perp is in W perp. So it seems to me we're going to need to know something about W perp first of all. And I guess the question is, should I do it the hard way or the easy way? How about the easy way? Okay. I mean, this is nice, right? This is my orthogonal basis for W. Now, to get V3, which would be orthogonal to these, I guess, you know, there's the calc way of doing it, right? So V3 you could get by doing V1 cross V2. So let me do that. You got what?
I got the answer splits it up as one vector plus another vector. I got the first vector.
Okay. But not the second one?
No.
All right, I'll look at it. The other vector is coming from here, okay? So V3, I'm going to get by dotting these things. 1, 1, 0. I'm cross product these things. This is one way to get it. This is cheating. I'm doing calculus instead of linear algebra. And I can't possibly do this if there's 4. But you guys said you want me to do it the easy way, and I kind of agree right now. Okay, so this equals 2i, and then minus 2j, and then let's see, a half plus a half is 1. So plus k. This is really a nice example. Wow, give Poole some credit. This is the vector 2, -2, 1. Is that really orthogonal to V1 and V2? Let's see. -1 and -1 is negative. Yeah, it really is. That's nice. Way to go, David Poole. Okay, so again, in MATLAB this would never work. But it worked. We got a really nice V3. V3 is orthogonal to either of these. So this is my basis for W perp. Okay? So Trent, you said you got the first vector. You got the little w.
I got, well, yeah, that one was negative 2 nines, 2 nines, and 8 nines.
Okay. To get little w perp, try taking V and projecting onto this.
Projecting on, so you said it's like U1?
Yeah, or V3, but just
Okay.
just project onto it, and that should do it.
Just that one, or do I have to?
No, that single vector ought to do it.
Okay.
Because that's then in V3. I mean, what's the picture? Let me show you the picture. The picture is I have a plane that contains the vectors x1 and x2. Oh wait, what's good about, well, we don't want x1 and x2. We want to take the same, let me show you the same plane. We had x1 and x2, but instead we take v1, which is the same as x2, and then we make sure that v2 is orthogonal to it. And then v3, of course, is orthogonal to that, because it's orthogonal to the entire plane. And so now, given V, you could project onto these things, and we'll have it. So W is the projection of V onto W, capital W, and W perp is the projection of V onto, well, that 2, negative 2, 1 ought to do it.
So yeah, that works.
That does work?
Yeah.
Okay.
It's me the other path. But now, we use the cross, like, are we supposed to use the cross product?
Oh, that's a good question. What are we really supposed to do? So what we're really supposed to do is use Graham-Schmidt. Because all I have to do is assign problem 6 instead of problem 5, and we're out of luck. Right? You could project and get the W by projecting onto these V's, but you wouldn't get W perp. So, that worked, but what are we going to do for real? Well, I'll show that on the next page. Here I go. And again, I guess I got to start over again. I had x1 was 110, and I had x2 was 342, right? And then you guys, using Graham-Schmidt, gave me V1 is also 110, and you gave me V2 was, remind me?
Negative 1/2, 2.
Oh, yeah. So how do you get V3? Well, we could use Graham-Schmidt, but we need an x3. Does it matter what you use for x3? No.
It's not.
As long as it's not in the span of these two. So you need something that's linearly independent. And so I know, for example, if I were looking at this, I might just take 1, 0, 0. I can very easily put that over here and see that it's linearly independent, because just look at the form of the matrix, right? If you had 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, and 3, 4, 2, it's already in row echelon form. So I think that's what I would pick. And then I need V3. So I need to get this orthogonal to these two. So how does that work? Well, Graham-Schmidt says that V3 will be, how's it work? X3 minus the projection of X3 onto W, right? And so what it really equals is X3 minus stuff times V1 and minus stuff times V2. And what's the stuff? Yeah, this one's V1 dot V1 in the bottom, and it's V1 dot X3 here. And this one's V2 dot V2 in the bottom, and it's V2 dot X3 here. And that's what you do. Good that I want to record it for the television audience. You said, why is the final answer written as a sum? And notice I said we were going to do it. I said we're going to write it as W plus W perp. Those are vectors being added. But I want to show it to you on my really exciting picture. Because if you actually were to draw what's going on here, that I'm going to pull out for this. All right, so we know that V is W plus W perp. Because it really is. What did we do? We projected V onto V1 and V2. And when we did that, well, okay, Projecting onto V1, I maybe got this, and projecting onto V2, maybe I got this. But those are orthogonal, and so I know that when I add them, when I add vectors, I really do get, this is W. And it really is the shadow, the projection, the orthogonal projection of V onto big W, onto the plane. And then if I project onto V3, right, that's really this one. This is W perp. And sure enough, you can see now that if I add W and W perp as vectors, I get V. Okay?